So who's excited to be here this morning? Raise your hand. Oh, we got actually a few. You're nuts. Okay. Hey, I'm glad that at least somebody's excited to be here. Um, it's always good to be here, right? I had the unfortunate duty yesterday of having to watch at least a little bit of this, and it's like, gosh, I hate watching myself, and to some extent, you can always, I can see why people are always asking me, are you tired? Do you feel tired? I'm like, no, I'm not tired. I'm not a bubbling fountain of energy. Let's put it that way. But all right, so end of the class, starting about 10:30, 10:35, something like that. We'll hand out the quiz for the online students. By about the time that you see this, it'll be around 10:50 Eastern time, and the quiz will be opened up. You have your option of taking care of all of this stuff, watching the video, then doing the quiz. You have until 9:30 tomorrow morning to get it finished up. So. In the way of announcements, there was a little bit, excuse me, there was a little bit of problem with the media site server last night and potentially continuing on until this morning. So if you were trying to watch that, you'll either need to look at iTunes or we've got some different feeds up for the moment. So not the cool one, but at least some way to get the information. So I got a few more homework or quiz zeros taken care of yesterday. Got a few more. You've got another week to get it done, so it's not like there's a huge rush. But at the same time, I will be heading back to my office, getting all of the things off the floor so that the maintenance people can come in and wax the floor of my office on Monday morning, and then I will be gone for the rest of today and all of tomorrow. So my internet access will be probably non-existent during that time. So if you need something, you can send an email and I will try to get at it, but you never know whether that will work or not. So any questions or concerns about anything? Yeah.
On the homework. Number 26, there were the voltages, the dependent and independent sources with the circles and the diamonds. What does that impact? How you are kind of combining them and things like that?
Let's see can I borrow your book there for a second? So 26. If you know when in terms of doing those kinds of problems, let's draw it up real quick. There's the general rule of thumb for all of these dependent source problems is always going to be write it up as if they were independent sources to begin with. Make sure you have an idea of what the controlling equations are for each of the dependent sources, and then sort it out later. And that's going to be the general rule of thumb for making this happen. So dependent source minus plus another dependent source. Okay. What a ridiculous problem. And so 12 volts across that one. There is some voltage Vx across that one, and it is a 4 ohm resistor. This is a 4Vx voltage source. This is a 2 ohm resistor. This is a 2VA voltage source. And then the voltage between here and here is what VA is. So that's the problem set up. So if we start writing, the key thing here will be to start writing the KVL equation, going around the loop. And again, we start out with the idea that the independent source, or all of the dependent sources, treat them like independent sources to start with, and just write it like it was that's just what the voltage was. So we reached the positive terminal of this first. So we have 12 plus, let's call it Vx since it's got a name already, minus 4Vx. Was there a special? I didn't have a special voltage across that. So for now, let's call it V2 ohms. That's the voltage across the 2 ohm resistor. And then we've got plus 2VA. And Kirchhoff's voltage law says sum around that loop is 0. So we can start doing a certain amount of combining of terms and start writing what we call the controlling equations, which are the equations that define what things like VA is and what Vx is. So the the easy one to write, at least to start with, is Vx. Because what is Vx? Vx is the voltage across this 4 ohm resistor. And what is the voltage across the 4 ohm resistor? Well, it's 4 ohms times whatever the current I is that's running through it. Then we want to write something for VA. So VA is the voltage from this 2 ohm resistor as well as the dependent source. So we've got that equals the 2 ohms of that times the current I plus another 2VA. 2VA. Sorry about that. So this one is nice and simple. We can go ahead and start plugging it back in places. Wherever you see a Vx in the original KVL equation, you can substitute this back in. Obviously, this one needs to be changed at least a little bit because we have a VA on both sides. So subtract 2VA from both sides. So a negative VA equals 2I, or VA equals a negative 2 times I. So now we have the important things. We've got the controlling equation for Vx, we've got the controlling equation for VA, and we've got a KVL equation that describes what's going on inside or in the circuit in general. And again, we wrote that original equation just saying, look, these dependent sources, we're going to treat them like independent sources and then sort it all out later. And that's always going to be the case when we deal with dependent sources. So now, from there, you should be able to solve it. You should be able to plug in wherever you see a VA, plug in the negative 2I. Anywhere you see a Vx, plug in 4I. And that should get rid of all of the variables. And the one other thing, I guess, that you need is that V2 ohms is obviously 2I. So now you've got one equation. It should be entirely in terms of one unknown, I. You should be able to solve for I and then find all of the other voltages that you would want to find. You can find out what Vx actually is once you figure out what I is by multiplying it by 4. Excuse me. The problem asks for a voltage that it calls V0, which is the same as whatever you solve for as 2VA. So once you've solved for I, you can solve for VA, and then you can plug that in and find out what 2VA is, and that gives you your V0. So again, the problem-solving technique that you're always going to use is to treat the dependent source originally like an independent source, then write the controlling equations in terms of other circuit parameters that you can solve for, then sort it all out. Start plugging those things back into your original KVL equation or KCL equation or whatever it happens to be. Any other homework questions? Pretty sure we'll be able to finish this up today, and so we'll go ahead and make that homework due on Monday morning. If you do have a question on it, please send me an email, and I will try to get out at some point and check my email, whether it's Saturday or Sunday or something like that. I'll be back on Sunday evenings sometime. So if you send an email, I'll try to get to it as quickly as possible. So, all right, we've got a last couple of slides to take a look at from Chapter 2, and then we'll start looking at the Chapter 3 stuff. But in the way of review, taking a look at those PowerPoint slides from yesterday, we've got single loop circuits that we solved for, started messing around with those to figure out what's going on in terms of how voltage divides across a couple of resistors in a single loop circuit with a single voltage source. And again, kind of the key thing, and I'm going to try to take advantage of the technology here a little bit. Key thing here is that we are interested in VR1, and that means that R1 goes on the top of the fraction, and then R1 and then the sum goes on the bottom. Similarly here, we're interested in R2, the voltage across that second resistor. So R2 goes on the top, the sum goes on the bottom. And that's kind of the key thing for voltage division, to remember that the resistor that we're interested in goes on the top of that fraction. But again, what you have to be careful of is to make sure that you have it in this form where there are only two resistors on the bottom, or else you need to use, I think, a slightly different version of the equation. This might work in a more general sense, but I wouldn't count on it. So don't work with it unless you're very comfortable. The question that we need to kind of answer is, what if we don't have just two resistors? And what if we don't have just one single voltage source like this one? If we don't have that, what do we do, and how do we kind of deal with that? So get rid of those. What we can do is we can combine voltage sources, and we just pay attention to the signs of the voltage sources as we run into them, and that allows us to combine them. And the key thing there is, just be consistent as you're going around the loop. What is the sign of what is the polarity of the voltage that you run into first? And that's each one of those voltage sources. And they need to be in series for you to be able to do that. Then what we also came up with is that we can reduce the network down to one or two resistors, whatever we want to do, by combining all of the resistors just in series and adding them up. Well, that's not at all where I touched. So we just start adding them up, R1 plus R2 plus R3, and we can combine them down into as many or as few resistors as we want to. And if we're interested in a particular resistor that might be in the middle of 3, we can combine the two on the outside, and that works out mathematically. It doesn't change the rest of the work on the problem. We got into single node pair circuits, where we're looking at a single pair of nodes that are sitting with some elements in parallel, and they are in parallel because they share those two nodes in common at both ends. When we write the KCL and start doing the rest of the work on that, we find that we get this general case that if you want to create an equivalent resistance for a bunch of parallel resistors, you combine them reciprocally. You put 1 over R1 plus 1 over R2, so on and so forth, and that gives you 1 over RP. And if you want to find out what that resistance is, you do have to flip it. This one you can use if you have exactly two resistors. I never use that one myself because I like the first form of it better because it's more general. This one will always work. This one only works when you have two resistors that you're trying to combine. Let's see. So that was current division between two resistors. We're trying to find out you have some sort of source that's generating some amount of current. What is the current that's flowing through each one of those resistors? In this case, we're going backwards. We say here is a particular we want to find out the current rolling through resistor 1, and we put resistor 2 on the top of the fraction and the sum on the bottom. Similarly, I2, we want to find the current running through the second resistor, R2, we put R1 on the top, and the sum of them on the bottom. And that tells us the fraction. And what you should see in this case is that current does indeed follow the path of least resistance. The smaller resistor is going to see more of the current running through it. We can combine current sources if they are in parallel. The one thing that we ran into yesterday that was kind of interesting was we had a circuit that had one current source going like that, and there was a resistor, and then there was another current source going the opposite direction. And those will end up kind of canceling out each other out instead of reinforcing each other as it might appear. And again, the key here is that we have a current flowing into the node like this, and we always give that the negative sign. And this one is flowing out of the node, and that one we give a positive sign to. So we take that into account when we start combining these current sources and giving them signs to actually combine them. Combining resistors, we started looking at this, was about as far as we got yesterday. When we want to combine an arbitrary number of resistors in series, we just add them up. When we want to add them in parallel, we combine them reciprocally. In general, what that means is that series resistors increase the amount of resistance and parallel resistors decrease the overall resistance. Just kind of a takeaway message there. So we've got one more example that I want to do of resistor combinations, and then I've got one exercise for you guys to try here in class. So, all right, one more. So we've got a circuit, a bunch of resistors. We want to find out what the equivalent resistance is seen by the input terminals. A and B. So what is the equivalent resistance as seen from those terminals RAB? We've got a 6 kilo ohm resistor here, we've got a 3 kilo ohm resistor here, 18 kilo ohms here, 6K here, and 10K here. Now this one I think is perhaps somewhat more straightforward than the example that we did at the end of class yesterday, because these are pretty clear as to exactly what's going on in the configuration that is in this circuit. The 3 and the 6 are obviously in series with each other, and that series combination is in parallel with this 18K resistor. And once we're done with that combination, what we'll just have are 3 series resistances, a 6, a 10, and whatever this big mess turns into. So this is a little bit more straightforward than the example that we did in class the other day. So let's start working on that. The first thing that we'll do is we'll combine the 3 and the 6 into a 9K resistor. And so we will have 9K that's in parallel with 18K, so that means to find the overall parallel resistance, we'll have 1 over Rp equals 1 over 9 plus 1 over 18. Just in terms of a shortcut, you obviously don't need to put in the 1,000 part on these things, because 1 over 9,000 plus 1 over 18,000, and you flip it, just as long as you remember, yeah, we're working in kilo ohms here. You can save yourself a little bit of time. So 1 over 9 plus 1 over 18, flip that, and that combines for a parallel resistance of 6 kilo ohms. So what that means is this final version of the circuit, after combining this whole big mess, we have a 6K resistor, our equivalent resistance of another 6 kilo ohms, and then a 10 kilo ohm resistor from the original network. A, B. And now it's a simple matter. You've got 3 series resistors. Add them up. So you have 6K plus 6K plus 10K, and that's 22 kilo ohms of resistance. So no surprises on that one. Pretty straightforward. The ones on the homework are somewhat more challenging, but that's kind of the point of the homework in my opinion. So, but here's one more that you can do. I want you guys to work on this one a little bit. It's a little bit more in line with the difficulty of the homework questions. 8 kilo ohms, 4 kilo ohms, 12 kilo ohms, 3 kilo ohms, 4 kilo ohms, 6 kilo ohms. Got two terminals A and B, so find the equivalent resistance. RAB is found looking in from those input terminals. So take about 3-ish, maybe 4 minutes to work on this one, and we'll come back together and look at it. So it looks like most people have something approaching an answer, and we'll start working through this step by step. Step 1, combine the 4 and the 8 in series. So that turns into a 12 kilo ohm resistor. Step 2 then is that we've got this 12K resistor in parallel with this 12K series resistance. So that's 1 over 12K plus 1 over 12K equals 1 over their parallel resistance equivalent. So 1 over 12 plus 1 over 12. Flip that. Again, we get 6. So now we could redraw the circuit and say, all right, we've got 6. We've got 4. We've got 3 here. And now we're down to just a 6K resistor here. 6, 3K, 4K. Now, the tricky part of this one is going to be, what do you do here? And what you can see is that we've got this node here, and we've got this node here. And if you really break it down, what's very clear is that the 3K and the 6K are in parallel with each other, and that parallel combination is in series with the 4K resistor. So we've got the 1 over 3 plus 1 over 6. And I've had students in the past who could do those things in their heads, and I just don't know how they do it. So that gives us a half, and so the equivalent resistance of the 3K and the 6K is a 2K resistor. So now we're down to original 6K resistor here, a 4K resistor, and a 2K resistor. So obviously the 4 and the 2 are in series, 6K in parallel with 6K, 1 over 6 plus 1 over 6, it's 2 over 6 or 1 over 3. And so the equivalent resistance, RAB, equals 3 kilo ohms. Anything too surprising in that one? Okay. So we've learned enough at this point to actually do some amount of circuit analysis. And this is perhaps the strangest possible way to do this analysis and the longest possible way to do it, but we can do circuit analysis with what we know. So let's do a quick example. So here we've got voltage source, resistor, just build out this network, single source, a whole bunch of resistors, 3K, 9K, 4K, 3, 6, 9, 12 volts, I1, I2, I3, I4, I5. And then VA is the voltage across the 6K resistor, VB be the voltage across the 4K resistor, and BC is the voltage across the 3K resistor, or in other words, those three resistances. But the circuit diagram, I think, is messy enough as it is, so I don't want to try to make it any worse. So we want to find all of the labeled voltages and currents. We want to find VA, VB, VC. We want to find and all the I1, I2, I3, I4, I5. So, and we can do this. You guys possess enough skills, even if you didn't come into this class with any other circuit analysis skills, we can do this. And again, like I said, it's kind of the longest possible way to do it, but we can do it. And here's how. We take and we say, all right, 9 is in parallel with 3, or 9 is in series with 3, so that gives us a total of 12. In parallel with 4, so we'll reduce that down to 1 over 12 plus 1 over 4. Flip that. That gives us 3K resistance. So this all combines down to 3. We had 3 in series with 3. So that's 6 in parallel with 6. 1 over 6 plus 1 over 6. Flip that. Again, we've got 3. So we've got 12. What this reduces down to in its very simplest form, well, perhaps it's not simplest form, is a 9K resistor and then a 3K equivalent resistance. And that's what we can bring it down to at its absolute simplest level. And I think that you guys are comfortable enough with the combinations that we've done here. These were in series, that was in parallel with this. That ends up being in series with the 3K resistor, which is in parallel with the 6K resistor. Reduce that down, you get a 9K and a 3K and a 12 volt source. Now, there's one really, I guess, kind of interesting or vaguely exciting thing, which is that the voltage that's across this 3K resistor is still VA. It's still the same voltage that was across the 6K resistor. And that's kind of cool. And it's something that we can use to help us out. You know, if you don't want to use it that way, you don't have to, but that's how it ends up working fundamentally. And so we can use a simple voltage divider to find out what's going on. Or we still need to solve for I1, so we can kind of do it however we want. what you can look at and start to work out in your head without a calculator is that we've got 12 kiloohms of overall resistance and a 12-volt source. And so this original current I1 is going to be 1 milliamp. And that you can kind of do without a calculator. 9 kiloohms, 3 kiloohms, 12 kiloohms of total resistance, 12-volt source, 1 milliamp of current. And so the voltage VA will be the current I1 that's running through that 3K resistor, equivalent resistance, times the 1 milliamp of current, which gives us 3 volts. So now we have to kind of work backwards from where we were and start taking what we know to find out the rest of the parameters that exist in the circuit. So to solve for I2, we know that I2 is going to be, we know that all of the current I1 comes into this node, and then I2 and I3 leave. And so the sum of I2 plus I3, we'll use that in a minute. I'm getting ahead of myself. To solve for I2, we know that it's going to be the voltage that's across the 6K resistor divided by the resistance. And we know what that voltage is. It's 3 volts. So we have 3 volts over the 6K of resistance. Therefore, I2 is 0.5 milliamps. Again, that's because the voltage across this equivalent resistance is the same as the voltage across the 6K resistor. So we take that known voltage divided by the known resistance to find the unknown current I2. Now we can pretty simply figure out what is the voltage across or what is the current I3 by saying we know what I2 is, we know what I1 is. So if I1 is 1 milliamp and I2 is 0.5 milliamps, well, how much must I3 be? Well, it's the other half a milliamp. So I3 is the other 0.5 milliamps. So we've gotten a couple of things solved for here at least. We've got we have VA solved for as 3 volts. We have I2 solved for as a half milliamp. We have I1 solved for as 1 milliamp. We have I3 solved for as a half milliamp. So now we need to look at a slightly different version of the circuit to kind of help us out. And it's going to be a partially reduced version of the circuit and not a fully reduced version of the circuit. So one of the first things that we did, and we didn't show the work for this one, we had resistor 3K, and then we had a series resistance. So this is the original 3K from the circuit. This is the original 6K. This is the original 9K, original 12 volts. And we have an equivalent resistance here that was, what did that end up being? It's the 9K and the 3K in series, so 1 over 12 plus 1 over 4. So that was a 3K equivalent resistance that we reduced the circuit down to in one of our first steps. So one of the things, and so we know that we figured out that I1 was rolling through at 1 milliamp, I2 was a half milliamp, I3 was also a half milliamp. So we can find out this is still VB, even though it's been reduced, it's still that same VB voltage that was across this 4K resistor in the original circuit. And so if we want to find out what VB is, we multiply the 3K of resistance times the 0.5 milliamps of current, which gives us 1.5 volts. again, we can do the same thing that we did here and say, well, if we want to know the current that's running down through here, if we know the voltage that's across it, which is the 3 volts that we solved for in the first place, divided by the resistance, that gives us the current. So, and that's going to be, and we're going to solve for I4 that way. I4 is the 1.5 volts across the original. In this case, we're going to do, we need to use the 4K of resistance to find out the appropriate voltage. Or 4K resistor. So 1.5 volts divided by 4 kiloohms gives us 0.375 milliamps. So now we've got a bunch of stuff that we need. I3 is going to equal I4 plus I5. That's doing the KCL at this node. We've got I3 coming in, we've got I4 and I5 leaving. So we know I3, we solved for that one, it's a 0.5 milliamp. We just solved for I4 as 3.75 milliamps, so I5 equals a 0.5 milliamp minus 0.375 milliamps, which is that 0.125? So it's 0.125 milliamps. And the last voltage that we need to solve for is VC, which is going to be that current I5, or 0.125 milliamps, times the resistance of 3K, which is something ridiculous. 3 times 0.125, which is 0.375 volts. So, what we did in that example is we put together all of the things that we've learned and used them in these various weird combinations to do to analyze what is actually a very trivial circuit. We took and we did a bunch of resistor combinations to bring this complex kind of looking circuit down to something very simple so that we could start solving for quantities. And then once we did that, we basically just kept using KCL and Ohm's law to figure out what the rest of the values were. So we used Ohm's law to figure out what the current was rolling through the single loop version of the circuit. And that allowed us to solve for the voltage VA across this equivalent resistance. From there, we could figure out what I1 was, and we also were able to figure out what I2 was just by dividing that voltage by the resistance. KCL gave us what I3 was, and then we started using Ohm's law again. What is the voltage that's across some of these other things, including what the voltage was VB, which is across this equivalent resistance to start with. We found out what VB was, which allowed us then to use that value to solve for I4. Once we knew I4, we could solve for I5 using KCL, and then again, just Ohm's law gives us VC. So it's you can do it using all of those things. This is an incredibly inefficient way to solve a circuit. And I think what we may get to today, we'll certainly get to on Monday, is looking at nodal and mesh analysis, which gives us a much easier way of analyzing these circuits without squishing them down to something ridiculously small like this and using this bizarre combination of things to make it work. But I guess the important thing is now that you've been in circuits for 4 days, you can actually solve a circuit. So, hey, that's an upshot, right? I was looking through my notes during when you guys were working, and interestingly enough, hey, this is all the stuff about dependent sources that we already talked about, where when you want to deal with dependent sources showing up in a circuit, you start writing out the KCL or KVL equations as if the dependent source were independent, and then write what we call the controlling equation that specifies the relationship of that dependent source to some other circuit quantities that we can solve for, a loop current or a voltage somewhere else on across the resistor or whatever. And then use those equations, plug them back into your original KVL or KCL equation, and solve for the unknown quantities. And that's all we do. We did one example, so let's do let's just do one more example. We did one example of a single loop. So let's do a KCL example instead. So here is the circuit, the current source, 2 resistors, another resistor here, and finally we've got a dependent current source. Right. So that's our circuit. This is current source that produces 4 times I0 amps of current. The current I0 is what's coming down through this. And this happens to be a 3K resistor. Then we've got a 2K resistor, and we've got a 4K resistor. And then this is a 10 milliamp current source. Now, what we will do for convenience sake, for convenience of the analysis to make it work, is to say, all right, all of these things are in parallel, at least each one of these things between the pair of nodes on the top and bottom are in parallel. Technically, we need to combine this 4 and 2K resistor to get something that's totally where everything is in parallel with each other. But across each one of these branches, let's introduce, and this is just for purposes of analysis, is to say, well, let's call that Vs. That is the voltage across each one of these parallel branches. And the reason that we're going to need that is that we don't really have any other way of expressing what I0 is. Because we need, kind of the bottom line here is that we have I0 as part of this dependent current source. And I0 is defined as the current that's rolling through this 3K resistor. And we need to be able to define that in some other way, some other circuit parameter. And so what we need is how do you define what the current is that's running through a particular resistor? Well, it's the voltage across the resistor divided by the resistance. And so we need this as an analysis tool. That's the sole reason that it exists. So let's write a KCL equation at the top node, which is all along the top, all throughout there. So we've got 10 milliamps of current that are leaving the node from our current source. So that's a positive 10 milliamps. Then we have, and let's just call it, call this I1. Again, purposes of analysis, not a big deal. We've got I0 that's leaving, also good. So we'll just call it I0. And then we've got 4I0 that's coming into the node from our dependent current source. It's coming in, so it's going to get a negative sign, minus 4I0. Now here comes the step where we need to have that analysis tool of that voltage, because we need to define what are I1 and what are I0 so that we have some sort of idea of what we can stick into these, at least those two parts of the equation. This one we also need to know. So I1 is the voltage that's across the resistance, which is that Vs. And then we've got, give it the total resistance of the 6K resistance, and that's what I1 is. I0 is the voltage that's across the resistor, or Vs, divided by the resistance of 3K. That KCL equation equals 0. Now, if we take and we plug all of this back in up here, let's do some simplifications. We can, terrible notes. We can solve for what Vs is, and that will give us all of the rest of the parameters that we need to find. And incidentally, the thing that we're interested in at this point is the voltage across the 4K resistor. That's what we're going to eventually solve for. And which means that we need to know what the current I1 is, and we need to, but anyways. So let's put this stuff back up into the original equation. Put the 10 milliamps on the other side. Let's turn this already into negative 3I0. So we've got I1 minus 3I0 equals a negative 10 milliamps. So plug stuff in. We've got Vs over 6K minus 3 Vs over 3K equals a negative 10 milliamps. So if we, what I've got in my notes is trying to simplify this as a fraction, and what it works out to be here is you've got a negative 5 Vs over 6K equals a negative 10 milliamps. And you get that by, multiplying, getting the common denominator of 6K, which makes this a negative 6, and then you've got negative 5 on the top. So you get, that's what the fraction ends up being. Multiply both sides by 6K, so you get negative 5 Vs equals 6K, so 6,000. I feel like I should trust my notes, but at the same time, I'm not trusting it, yeah. So that's negative 60. And so then Vs equals 12 volts. So once you figure out, well, there's 12 volts across that, the current I1 that's running through there is going to be, well, what you can actually do here is you can apply voltage division. And it has nothing to do with the fact, well, we don't actually have a voltage source anywhere in the circuit, right? But you can still apply voltage division across these two resistors because we know that between these two nodes, there's 12 volts across it. So we want to know what the voltage is in the 4K resistor. We called it V0. That's based on the 4K resistor. We're doing voltage division, so we put the one that we're interested in on the top, 4K, over the total 6K. Multiply that by 12 volts. And you get the same answer if you say, well, I know that I've got a current I1, and I multiply that by 4K, and that's going to give me my voltage. Both of them will give you the same answer. So 2/3 of 12 is 8 volts. So again, and I will say it a lot during the course of the semester, is that the way that we analyze circuits containing dependent sources is to first treat them like they were independent, write out the KCL and KVL equations. Later on, it's going to be write out the node and mesh equations, treat them like they're independent, and then write the controlling equation, and then substitute it back in. Deal with it all later at that point. So there are some more examples that we could do, but I think rather than trying to get started on anything else, we'll just kind of sum this stuff up that we talked about in this chapter and then do the quiz and maybe let you guys go a couple minutes early. So let's sum up with the last couple of slides here. Key things to take away from Chapter 2, Ohm's Law, V equals IR. The voltage across the resistor is proportional to the amount of current that's running through it. Kirchhoff's current law says that the algebraic sum of all the currents entering a node is 0. We're going to think about it perhaps more in terms of all of the currents that are entering a node equal the sum of the currents that are leaving the node. And to facilitate the algebra working out, all the currents entering the node are going to get a negative sign. All the currents leaving the node are going to get a positive sign. Kirchhoff's voltage law says the algebraic sum of all the voltages around a closed path is 0. So just sum up the voltages as you encounter them. As the first terminal that you run into on a particular voltage is going to give you the algebraic sign for that voltage. Solving a single loop circuit, the easiest thing to do is if you need to find out all of the parameters, you can determine what the current I is by using KVL and Ohm's law. which basically boils down to find out what the overall resistance is and divide that source voltage by that resistance. Solving a single node pair circuit revolves around KCL, writing an equation that determines all of the currents that are rolling in there. And then remembering, in the case of our last example, that it might help to introduce an additional analysis voltage, remembering that all of the elements that are in parallel have the same voltage across them, just like everything that's in series has the same current running through it. Voltage division, we divided by two series resistors directly proportional to the resistance. In other words, the larger the resistance, the larger the voltage. We put the resistor that we're interested in on the top of the fraction. We put the sum of the resistances on the bottom. Current division is divided between two parallel resistors inversely proportional. In other words, the larger the resistance, the less current that goes through it. In terms of equivalent resistances, we add up series resistors, just add them. We add up parallel resistors reciprocally so that they so your overall resistance will go down a little bit. So, short circuit, resistance equals 0. You plug that into Ohm's law and you see that there's no voltage across the short circuit. Open circuit is an infinite resistance. Again, plug that into Ohm's law. You see that there's no current running through an open circuit. That's it for my prepared material. You certainly have a few minutes if there are any questions before we do the quiz, or I can hand it out and you can go to it. Bring it on. Bring it on. All right. So, online students, make sure that you take the quiz sometime between now-ish and tomorrow morning at 9:30, and that's going to be the general pattern. Homework is definitely going to be due on Monday morning at the beginning of class, so bring that in. Online students, I will send out an email on exactly what I'm going to do on that. All right, let's do it.